For a long time, the CPU was the most important chip in any computer. Every decision went through it. Every instruction came from it. The GPU was just there to draw things on screen, nothing more. But today, that has changed completely. The GPU is no longer just drawing pictures. It is thinking, learning, and making decisions on its own. And because of this big shift, the CPU has lost its top position, at least when it comes to creating images on your screen. This change did not happen overnight. It built up slowly over many years, and now we're at a point where the old way of doing things is being left behind for good. To understand this change properly, we need to go back to the very beginning. When you play a video game, two chips inside your computer are working together as a team. The first chip is the CPU. Its job is to figure out everything that is happening inside the game world. Where are the players standing? What direction are they moving? What do the physics look like? What is the weather doing? What is the enemy AI thinking? All of these questions are answered by the CPU, and it does this work thousands of times every second. Once the CPU has figured all of this out, it sends instructions to the second chip, the GPU, and tells it to draw everything on screen based on those instructions. The GPU is extremely fast at drawing. It can handle millions of triangles and pixels at the same time. But for most of history, it always had to wait for the CPU to tell it what to do. The GPU had no mind of its own. It was powerful, but not smart. It was like a very fast worker who needed a manager to tell them every single step. The CPU was that manager, and the GPU followed every order without question. This whole process, where the CPU controls everything and the GPU just draws what it is told, is called native rendering. Every pixel you see on your screen was the direct result of a CPU instruction being carried out by the GPU. It was simple, predictable, and it worked very well for decades. Games got better, looking every few years, simply because both chips got faster. The CPU gave smarter instructions, and the GPU drew them more quickly. The system was balanced, and everyone was happy. But then, games started trying to look truly realistic, and the old system started to crack. Real life is full of incredibly complex lighting. When sunlight comes through a window, it bounces off the floor, hits the wall, reflects onto the ceiling, and creates soft shadows in every corner. Simulating all of that mathematically, in real time, for every single frame, is an enormous amount of work. Traditional rendering had to fake most of it, using clever shortcuts. The results looked decent, but never truly real. And as players and developers kept wanting better graphics, the shortcuts were no longer good enough. NVIDIA understood this problem and began working on a new approach. In 2018, they launched their RTX series of graphics cards, which introduced ray tracing. Ray tracing is a method that actually simulates how light travels and bounces in the real world. Instead of faking lighting with shortcuts, ray tracing traces the path of millions of light rays and calculates exactly how they interact with every surface. The results were stunning. Reflections looked real, shadows had soft. Edges and rooms felt genuinely lit. But there was a serious problem. Ray tracing was incredibly slow. Running it at full quality made even expensive graphics cards struggle to reach smooth frame rates. To solve the speed problem, NVIDIA introduced DLSS, Deep Learning Supersampling. DLSS used a trained AI model to take a low-resolution image and make it look like a high-resolution one. Instead of the GPU drawing every pixel at full detail, it drew fewer pixels, and then the AI filled in the rest intelligently. The AI had been trained on millions of images and had learned what high-quality images look like, so it could make a rough image look sharp and clean very convincingly. The performance savings were massive, and the image quality was surprisingly good. For the first time, AI was playing a real role in how your screen looked, but DLSS was still just a helper running on the side. The core rendering pipeline was still the same old CPU and GPU team working together the traditional way. Then NVIDIA introduced neural shaders, and that is when everything truly changed. To understand why neural shaders are such a big deal, you first need to understand what a regular shader is. A shader is a small program that runs on the GPU and decides how a surface should look. When light hits a wooden floor, a shader calculates the color, the shine, the roughness, and the shadows based on fixed mathematical rules. When light hits a piece of glass, a different shader calculates transparency, refraction, and reflection using more math. These calculations happen millions of times per frame for every surface in the scene. They are fast, but they follow strict rules and can only do exactly what the math allows. Neural shaders replace those strict math rules with a trained AI brain. Instead of calculating the answer from scratch using formulas, the AI has already seen thousands of examples of how different surfaces behave under different lighting conditions. It has learned the patterns. So when it needs to decide how a surface looks, it does not calculate. It remembers. It looks at the situation and says, based on everything I have learned, this is what it should look like, and it produces the answer almost instantly and with stunning accuracy. This approach can handle incredibly complex visual effects that would be very expensive to calculate the traditional way. The soft glow of light passing through human skin, the way velvet looks different depending on which direction the fibers are facing, the shimmer of light on a puddle of water at night. All of these things require heavy math if done traditionally, but a neural shader can approximate them with a small AI model that runs very efficiently on the GPU's tensor cores, special hardware inside RTX cards built specifically to run AI calculations at high speed. The result is that the GPU is now doing something completely new. It is not just executing instructions. It is using intelligence to fill in details, approximate reality, and visual information that was never explicitly calculated by anyone. And this is the exact reason why the CPU has become secondary in the rendering process. Calculated draw calls kept the GPU busy with a constant stream of instructions. The GPU depended on the CPU completely, but with AI running inside the GPU itself, much of that dependence has disappeared. The GPU can now look at a scene, understand what is in it, and make intelligent decisions about how to render it, all without waiting for the CPU to figure things out first. NVIDIA's frame generation technology made this even more dramatic. Frame generation, which is part of DLSS 3, uses AI to create entirely new frames that the CPU never calculated. The game engine never simulated these frames. The physics never ran for them. The CPU never sent any instructions for them. The GPU's AI simply looked at the frames that came before and after, and figured out what a new in-between frame should look like. It then inserted those AI-generated frames into the output, making the game feel smoother and faster. The CPU had absolutely no role in creating those frames. They were born entirely inside the GPU, from AI alone. This is a historic shift. For the entire history of video games and computer graphics, every frame on your screen started its life as a CPU instruction. The CPU was the origin of every image. Now, entire frames are being created by AI inside the GPU, with the CPU never knowing they existed. Native rendering, the idea that every pixel comes directly from CPU-controlled calculations, is no longer the full story of how your screen works. For game developers, this new world brings big opportunities. Complex lighting and material effects that once required months of manual optimization can now be handled by AI models. Development becomes faster and the results look better. But there are also challenges. AI is harder to debug than math. When a neural shader produces a strange result, figuring out why is much more difficult than fixing a broken formula. And since all of this requires tensor core hardware found only in RTX cards, not every player can experience these features yet. Still, the direction is absolutely clear. Every new generation of GPU hardware is more AI capable than the last. Every new game engine is adding more neural and AI-driven features. The role of the CPU in rendering is shrinking with every passing year. And the images on our screens are increasingly the product of a GPU that thinks, learns, and creates, rather than a CPU that simply gives orders. The CPU is not finished. It still runs the game world, handles the story logic, manages the audio, and takes care of networking. But when it comes to the specific job of putting pixels your screen, it is no longer in charge. The GPU, powered by neural networks and AI, has taken over that responsibility completely, and more realistic than anything the old CPU-driven native rendering pipeline could have ever achieved on its own.